Moments of inertia, type 1, angular velocity. So this is the example 14.1 on page 240 in Oliver Murphy's book. And we're asked here to find the angular speed of the system when the rod is vertical, where we have a rod of length 2L and mass m, and a disc of mass m and radius L attached to the rod, so that the rod is along the line of the diameter of the disc, and we have to find the moment of inertia of the system about an axis through P, which is perpendicular to the plane of the disc. So if we were to draw what that looks like, we would see that we have the rod passing through the diameter of the disc of length 2L, and the disc has a diameter of 2L. So in other words, if I mark in C the centre of my rod, then this would be L, 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 and L. So what we want is the axis of rotation to be through P. And then what we're going to do is the system is going to be free to rotate around the horizontal axis at P, which is perpendicular to the plane of the disc. In other words, if it's released from rest when the rod is horizontal, it will then rotate to the point where the rod is vertical. In other words, we can see here it'll move from position 1 to position 2, so the rod is going from horizontal to vertical. And then we want to basically find the angular speed when the rod is vertical, because obviously if it goes from position 1 to 2, you would expect it to continue past position 2 and then possibly fall back down, or if it had enough momentum, it would continue to rotate in a circle. So all we're doing is finding the angular velocity as it passes through position 2. So the first thing is to find the moment of inertia of the system. So we're going to get the rod through P, and of course that's going to be the moment of inertia at the end of the rod, so 4 over 3 ml squared. We know that the mass of the rod is m, and if we go from the centre to the end of the rod, that's just going to be L, so we actually just end up with 4 over 3 ml squared. We're not getting anything different there. Now what we have to do is get the moment of inertia of the disc, but we have to get the disc through P. So first we have to get the disc through C, and then if we were to place our pencil at C and our pencil at P, and if I was to do it kind of looking at it from this position, we would see that P will be parallel to C. So we'll have to use the parallel axis theorem. In other words, I'll get the moment of inertia through C and then add on md squared to get the moment of inertia through P. So again, you can work those out separately, or you can do it all in one go. I'm going to do it all in one go here. So we have the moment of inertia through C for a disc is a half ml squared, and the mass of the disc is m, and the radius of the disc is L, and then the mass of the disc is m, and the distance from the centre of the disc to P, if I draw it on the diagram, I can see there is 3L, and I have to square that. So therefore that's going to be a half ml squared plus 9 ml squared. So the moment of inertia of the disc through the axis P is 19 over 2 ml squared. So therefore we say the moment of inertia of the system will be the rod plus the disc, and it's the rod through P plus the disc through P. So the moment of inertia of the system through the axis P is 4 over 3 ml squared plus 19 over 2 ml squared. So the inertia through P then as a total would be 65 over 6 ml squared. Okay, so our moment of inertia is always the first thing that we are calculating in these questions. So that should just come natural now at this point after doing that worksheet last week, when we were working on the basics. Okay, so part 2 then says, if the system is free to rotate about the horizontal axis of P, find the angular speed when the rod is vertical. So I'm going to put that diagram here again on page 2. So again, I'm just going to mark in the centre of my disc. I'm going to mark in centre of the rod. So we said the rod was L, L, and the radius was L. So we have L, L, and L. And let's see there. So what we want to do is mark our standard position. So we always take our standard position through the centre of gravity of the lowest part of the system. So I'm taking through the disc's centre. So if you just say standard position is the line through the centre of gravity of the lowest part of the system. Okay. All right, so we need to look at, well, what is the height of the centre of gravity of the rod and the centre of gravity of the disc with respect to the standard position before and after its starting and end position. So here's my start and here's the end. So of course at the start, the height of the centre of the rod to the standard position, and also the height from the centre of gravity of the disc to the standard position, we can see, if I mark it in green here, is going to be 3L. Whereas if we look after, the height of the rod, so the centre of gravity of the rod to the standard position, I can see is 2L, whereas the centre of gravity of the disc to the standard position will be 0. Okay, so we're going to use our conservation of energy. So we say beforehand, we have our potential energy plus our kinetic energy. So our potential energy of the rod will be mgh. And then we'll have the potential energy of the disc plus the kinetic energy of the system. So because it's rotating, it'll have angular velocity. And therefore we're using a half I omega squared. So I'm just making sure I'm noting that I'm talking about the disc, the rod, or the system. So if we sub in our values, we're going to have the mass of the rod, which was m by gravity, by the height of the rod above the standard position we've said there is 3L, plus the mass of the disc, which is m by gravity, which is g, by the height of the centre of gravity of the disc to the standard position, which again we've said is 3L. Plus we have a half times the moment of inertia of the system times the angular velocity. But we're told that if we go back, it is released from... So it's the system is free to rotate and it's released from rest. So that's important there, released from rest. So therefore the angular velocity at the start is 0. So I don't even need to sub in what I is there because obviously anything times 0 is 0. So that'll give me 3mgl plus 3mgl, which is of course 6mgl. So we call that equation 1. And then we're going to do after. So again, after, we'll look at our potential energy and our kinetic energy. So again, we'll have the potential energy of the rod plus the potential energy of the disc plus the moment of inertia of the system. And therefore, if I sub in, we have mass by gravity, and we said the height, if I go back up to the diagram there, of the centre of gravity of the rod to the standard position is 2, and that should say 2L. 2L. And then we have mg, and the height of the disc, the centre of gravity of the disc to the standard position is 0, because obviously the centre of gravity of the disc to its centre is no distance. And then we have a half times the moment of inertia. Well, the moment of inertia of the system we said was 65 over 6 ml squared times omega squared. So if I simplify that, we have 2 mgl, and then we have plus 65 over 12 ml squared omega squared. So we'll call that equation 2. So because we have conservation of energy, 1 must be equal to 2. So we're going to say equate 1 and 2. So if I equate 1 and 2, we have 6 mgl is equal to 2 mgl plus 65 over 12 ml squared omega squared. So by bringing everything to one side there, we end up with 65 over 12, and I can see and M is gone, and we'll have 1L, 1L and 1L gone. So that's 65 over 12 L omega squared is equal to 6G minus 2G, which is 4G. So therefore omega squared is equal to 4G times 12 divided by 65L, which is equal to 48G over 65L, and therefore omega is equal to the square root of 48G over 65L. So if we knew what the length was, you could actually get an actual value correct to so many decimal places for omega. Or if we were looking for linear velocity, we might be given some information there. We'd multiply it by the radius of rotation then to work out what V is. Okay, so for the second example, we're looking at example 14.2 on page 241. And here we're given a uniform rectangular lamina of mass M, and it's 6L by 2L in its dimensions, and the centre of gravity of the rectangle is at C. So we're going to find the moment of inertia of the lamina about C first of all. And to do that, we need the moment of inertia around axis A, around axis B, and then around axis C. And of course, to do that, we'll use our perpendicular axis theorem. Because if we were to place our pencil at C, we would find that it would be perpendicular to the plane of the lamina itself. So this one would be our perpendicular axis theorem. And then we're going to be getting the moment of inertia through the axis at K. So again, if I was to place my pencil at K and I was to place my pencil at C, then what we would see is that C is parallel to K. So we're going to use our parallel axis theorem for part 4. In part B then, we're told a point mass is then attached at the point P, so the opposite end of the lamina to the axis point, and the system is then free to rotate about a horizontal axis through K. So it's like as if you stuck your pencil through the page at K and then released the page, it would rotate in a circular motion. But obviously, if it didn't have enough momentum, it would just oscillate back and forth like a pendulum. So we're told the system is released from rest when P is vertically above K, and we have to find the angular speed and the speed of the point mass when it is vertically below K. So the angular speed is going to be omega, and the speed is our linear speed, which is V. Okay, so let's get the moment of inertia first of all, right? So we're going to start with the lamina, and we have to get it through axis B, axis A, and then through C. So we can do it all in one go, or we can do it separately. So the perpendicular axis theorem states that it's going to be moment of inertia of A plus moment of inertia of B. And for the lamina, it's a third ml squared, which can be found again on page 53. So we have our parallel axis theorem, our perpendicular axis theorem, and we have no lamina formula in our tables. We have to remember that, but it's the same as the rod, right? So if I'm subbing in here, we're going to have the moment of inertia through C is going to be 1/3 ml squared. Well, the mass of the lamina is m. L through A, if we look over here at the diagram, is L. And then we're going to add on the moment of inertia around the axis B. So it's going to be 1/3 ml squared. But around the axis of B is going to be 3L squared. So the moment of inertia through C is 1/3 ml squared plus 9 ml squared divided by 3, which is 3 ml squared. And the moment of inertia through C is 10/3 ml squared. Okay, so through A it was 1/3 ml squared, through B it was 3 ml squared, and through C, using the perpendicular axis theorem, is 10/3 ml squared. So now we have to find it through K. So through K we're using our parallel axis theorem. So that's going to be the moment of inertia through C plus md squared. So therefore the moment of inertia of the lamina through K is going to be 10/3 ml squared plus the mass of the lamina is m, and then the distance d from C to K, again if we look at the diagram, from C to K is 3L. So that's 3L squared. So therefore that's going to be 10/3 ml squared plus 9 ml squared. So the moment of inertia through K is 37/3 ml squared. Okay, so now we have to look at the point mass. Point mass is going to be attached to the point P. So we'll draw a new diagram for this. Okay, so we have our point mass up here at P, attached to the end of the lamina. The lamina is rotated up to position 1, and then it's released from rest, and it's going to have angular velocity as it rotates to position 2, so that the point mass is directly below K. So let's just mark in the dimensions again on that. So we had 3L and 3L going down. So that's 3L and 3L. So I'm just marking in my axis A and B again, and then 3L and 3L. So we also have to mark in our standard position there. And the standard position is always taken through the lowest part of the system. But of course the lowest part of the system is at the very end this time, because obviously that's where our point mass is. So that's our standard position, where the point mass is. So the point mass is at the end of the lamina, and therefore is the lowest part of the system. So before we can work out our angular velocity, we also have to work out the moment of inertia of the point mass. And the point mass is just md squared. So of course, through the position K for the point mass, well, the mass of the point mass is 2m, and the distance from P to K, we can see there is 6L, and I have to square that. So then that gives us a moment of inertia of 72 ml squared for the point mass. So therefore for the system, if we add the point mass and the lamina together, then that gives us a moment of inertia through the axis K to be 37/3 ml squared plus 72 ml squared, which gives us a total of 253/3 ml squared. Okay, so if we get our energy beforehand, then we're going to have the potential energy of the lamina, I'll just say L, potential energy of the point mass, I'll say P, and the kinetic energy of the system, let's say S for system. And again, because it's rotating, it's going to have angular velocity. So if we look at the lamina first, beforehand, the centre of gravity of the lamina to the standard position, our H is going to be 9L. So the mass of the lamina is M times gravity times the length, 9L. The mass of the point mass is 2M times gravity times the height. So if we look at the height of the point mass to the standard position, we can see that that is 12L. And then it starts from rest. So again, it doesn't matter. I don't need to put in the moment of inertia here. We just have 0 times anything is 0. So we're going to have 9 mgl plus 24 mgl. And if I add those two together, that gives me a total of 33 mgl for our energy beforehand. And then if we look at after, so just come over here to the left. So again, we have mgh for the lamina, mgh for the point mass, and a half I omega squared for the system. So now if we're looking at the position afterwards, I'll use a different colour here, I'll use purple. And if we're looking at the centre of gravity of the lamina to the standard position after, I can see that H is going to be 3L. But for the point mass, obviously H is going to be 0 because it's on the point mass. So we have mg for the lamina times the length is 3L plus 2m for the point mass. So again, just be careful not to put in m there. And then 0 for the height. And then we have to put in our moment of inertia this time because we have angular velocity. So 253 over 3 ml squared we worked out times omega squared. Okay, so this is equation 2. So we're now going to take 1 and 2 and we're going to equate them. So our conservation of energy states that our energy before should equal our energy after. So we have 33 mgl is equal to 3 mgl. Oh, I forgot to finish that, sorry. 3 mgl plus 253 over 6 ml squared omega squared, sorry. Okay, so equating those, then we have 33 mgl plus equals 3 mgl plus 253 over 6 m squared omega squared. And I can divide across by m and I can divide across by L. And that leaves me with 33g is equal to 3g plus 253 over 6 L omega squared. So getting omega squared on its own then. So that gives me 253 over 6 L omega squared is equal to 30g. And therefore multiplying across by 6 divided across by 253L and getting the square root of both sides gives me 180g over 253L. Okay, so that's the angular velocity, but it also wants me to get the linear velocity. So V is equal to omega, or is our relationship. But we need to know, well, what is this or? So or is the radius of rotation. And if we remember when we were doing circular motion last year, if we have anything rotating in a circle, it's got angular velocity, but at any point along that, it's got tangential speed, right? And this would be or. So obviously the radius of rotation here is the length of the lamina, which is 6L. So therefore V is equal to our angular velocity, which we said was the square root of 180g over 253L. And then we have to multiply that by the radius, which is 6L. And really all I have to do there then is I can square the L and put it underneath the square root sign. Because obviously if I get the square root of L squared, it would be L. So to put the L into the square root, I would square it. So that would be 6 times 180G L squared over 253L. And I can, of course, simplify that L on the top with the L on the bottom, which would give me 6, that should be a 6 there, sorry. 6 times square root of 180G L over 253. Okay, so what I'm going to get you to do then is I've attached the exam questions. So you're going to hand in 1996. So that'll be assigned. And then to practice, you're going to do page 243. Question 6 for the rod. We're going to do question 8, which is a rod and a point mass.